between the physical sciences, the social sciences, maths, philosophy, a bit of economics in there. And it's targeted at those who are interested in climate change for sure, but also very much at those who might not be specifically interested in climate change, but who are interested in science more generally, in how academia works, and the power and the flaws of how academia works, particularly in relation to climate. So first and foremost, I would say it's a popular science book, and it just happens to be about something that is really societally relevant. So, to my mind, climate change, the study of climate change, raises many really deep and interesting questions about how we do science, how we do social science, how we understand the world around us. And these are really big, fascinating questions that are just as interesting, as fundamentally interesting as any in the sciences, whether that be the search for dark matter or the trying to understand the origins of consciousness. And in my view, these really big questions tend to get lost because of the social relevance of the subject. And what I wanted to do was bring these to the fore. I wanted to write a book that would appeal to readers who were interested in how these things fit together, regardless of their passion or their concern or indeed perhaps their fear about the issues around climate change. And my hope was that in doing that, it would help study many of these issues and provide better information, which would then go on to help us respond to the issues of human-induced climate change. So I'm guessing that most of you in the audience, and probably online too, are somewhat working in climate change circles. And in climate change circles, it seems to me fairly common to hear the phrase that really the science is settled, the science is clear, now it's time to act. So I think perhaps, for me at least, a good starting point is the science settled? Is it clear? And I think the answer is kind of yes, but also no. So I'd like to sort of unpack that a little bit. So let me step back a moment. When I started writing this book 7 years ago in 2016. And there were lots of books about climate change then, and there are vastly more now. There are an awful lot of books about climate change. My view was that most people going into a bookshop or going online looking for a book about climate change is already deeply concerned about the subject. They're deeply concerned about the consequences of climate change, or possibly in a few cases they think it's all a hoax. And what they're looking for is information to back up what they already know. In starting writing, what I very much wanted was not to preach to the converted. I didn't want to start from that point of you're picking this up because you already know that climate change is an issue. So I wanted someone picking it up to be drawn into the subject by the fascinating questions that are there. And in fact, when I first pitched the project to OUP, climate wasn't even in the title, and we've had a lot of debates about the title, but OUP wasn't going to let me get away without climate in the title. So, and they were quite right. So climate made it into the title again, but he wasn't there in the start. And the first few chapters of the book don't express any opinion about the societal issue. That's at least the concept. It doesn't even express an opinion as to whether climate change is real, whether it's important. The whole idea was to start from an agnostic point of view. But of course, it's a book about climate change. You can't get away with that. I realise I didn't take the time, never mind. You can't get away with that. I had to sort of come clean. So by 50 pages in, I had to come clean as to where I stand. And that makes something, particularly when it's going to be posted online, that makes it a little bit of a difficult talk to give, because in a sense, I'm giving away an early plot twist. The idea is you start not knowing this, and yet I've got to kind of give it away. Only it's not much of a plot twist, because anybody who knows either me or knows of the work that I've done over the last decade or so, knows my position on climate change. So by page 58, I've finished my 11 paragraphs. I've given my 11 paragraphs of why the reality and seriousness of climate change is really beyond reasonable doubt. 11 paragraphs is just ridiculous. It was 10 to start with, and 10 makes sense. Even 12 would be kind of nice, at least in an imperial measure. But I started with 10 and realised there was just one more thing that had to be in there to make the connections. So it's an 11 paragraph summary. I believe you need 11 paragraphs to summarise why climate change is seriously important. So with that as context, coming back to the question of is the science clear? Well, the answer is that the reality of human-induced climate change is clear. It's clear that from physical understanding, and it's corroborated by observations. And the series of the implications for the natural world and for human society, that's also clear from the good sound arguments there. So the existence of the threat and the character of the threat is really clear. Yet, despite that, there are many, many things in the study of climate change that are really not clear. There are many things that we don't know, and there are many things that we haven't really sat down, the academic institutions, academic researchers haven't really sat down and worked out what it is that we need to do, what's required to know them. So it's not just we don't know certain things, we don't know how to approach certain problems. We haven't sort of gone down to the foundations. So it's clear that we need to act, but nevertheless there's lots of things that we don't know, and that it would be helpful to know to help us respond the better to the threats that we face, to motivate the actions that we need to do. Now, in my view, academia is not well set up to address these problems. I think we need to highlight these problems, and we need to we need a kind of reworking of how a lot of the research on climate change is pursued. Now, that too is part of my book. Now, it seems the reason I say this is I think quite a lot of the research that we do on climate change isn't actually as responsive to society's needs as I think it needs to be. Now, for those of you working in the field, that seems like a pretty strange thing to say, because there's an awful lot of work that is targeted at being responsive to society's needs. There's an awful lot of funding that goes into giving answers to what we perceive as society's needs. But I would argue that an awful lot of the practically relevant work ignores some of the conceptual foundations of what we can know, certainly what we do know. And so it produces information that seems to be relevant and yet isn't necessarily as robust as it needs to be if we're arguing for a wholesale change in society. And on the other side, there is foundational work, particularly in the physics of the climate system, which I think I would argue is extremely robust. Only it doesn't really take account of the physical, of the situation we're in, the practicality of the changing state of the climate system. So while it might be robust in terms of of the science it talks about, it's not exactly relevant to human-induced climate change and to mankind's response to that. One of the many aims of my book was to bring these things together and to consider how different perspectives across different disciplines could help us generate information that is robust and relevant and better reflects our state of understanding across many different disciplines, and can really help us guide societal and policy choices and to motivate people throughout society to take part in that change, because I would argue we need to be looking at very large changes in the structures of our society, and that to motivate that requires honesty of information. It requires better information, but it requires us to be honest about the information. So my book presents a series of challenges across the social and physical sciences. Challenges regarding, for instance, what we mean by climate change, what we mean by climate, how we should define climate. So what does climate change involve in a way that can be applied to everything from a low-dimensional mathematical system up to the whole of the real-world climate system. Things about what the maths and economics and the physical sciences can tell us, how we communicate it, how we use the physical science information that we have in economic assessments, how we use social science understanding, how we should be using social science understanding of the societal problem in our design of the physical science research that we do, and how the structures of academia and of our research structures influence the conclusions that we draw and the chances of our success in providing useful information. But these challenges, I will present them later, but they're not as obvious as they seem. When you read them, they might seem somewhat obvious, but I would argue they're not as obvious as they seem. And to get our heads around why these are such big challenges, we need to ask questions of what is it we're trying to do? What are the characteristics of the challenge of what we're trying to do? And so the first section of my book goes through 7 characteristics that I would argue we constantly have to bear in mind when we're thinking about climate change. Particularly when we're thinking about the information we have on climate change, and specifically there I'm thinking about where we lack confidence. So I would say we have a really good understanding of the scale of the threat. That comes down to, in many ways, that there will be global warming, that there will be disruption, certain other aspects of the climate system we know. But here I'm talking about the type of information that goes down to local or national scale information. The sort of information that we might need to help us plan adaptation strategies. And the sort of information that it's not just about adaptation strategies, it's also about making climate change personal and relatable to populations. Because that is absolutely crucial in terms of motivating large-scale change. I don't really touch on this either in the talk or in the book, but things like the COPs, we've got a COP coming up next month, we have these international negotiations, we have a lot of animation about where the governments are meeting the challenges of what they have said they will do. I think my perspective on this is that it's great if they sign up to things, but they will only be able to do the scale of change that we're talking about if actually you have electorates that buy into that. If you don't have that, then a government can sign up, but they will just be voted out because the electorates will not sign up to it. So the electorates have to buy into it. And what is it that electorates need to see? And I would argue they need to see some information about how climate change will impact them and their society. It's how will our society change? And that brings us down to that kind of local information. We want that information, but that information is really hard to get. And that's kind of where my book and my thoughts and my talk fits in. So, I'd like to take you through the 7 characteristics as I have them. Does this work? It doesn't matter. So the first one is prediction. So I would argue that perhaps I would, you would say I would, but I would argue that the most crucial characteristic of human-induced climate change is that it's all about prediction. It's predictions that give us a choice in society. So we have some knowledge, we think we have some knowledge, we do have some knowledge about what the future will look like if we, for instance, achieve global net zero by 2050. And we have some information about what the world will look like if we only achieve global net zero by 2100, or maybe if we don't do anything to reduce greenhouse gas emissions. These are conditional predictions. I'm going to talk about predictions, not projections. We can talk about that later if you want, but that's what I'm going to do. It's this information that gives us a choice. Which future do we want? How much are we willing to pay to get it? What things are we willing to give up? Or you could reframe that more positively and say, how do we shift our perceptions of what we value in the light of the choices that we have? But it is in the light of the choices we have. So you can't choose do little today without choosing the future that goes with that. The two go together, and arguing for or against certain policies has to be done alongside the futures that correspond to that. So when I'm writing that and thinking about saying that, I'm thinking very much about the issues that have come up in the UK Parliament recently about, for instance, heat pump heating systems and electric vehicles. People get very animated about that. What perhaps frustrates me about some of those arguments is that they tend to be just argued as if you're just arguing about heat pumps. You're not. You're arguing about heat pumps, which impacts emissions, which impacts what the future is. And we need to relate that to the future it is. It's not just about heat pumps, because why would most of us care about heat pumps that much? It's the next stages that become really important. And it's scientific understanding that gives us this choice. And being clear about what we know is crucial in order to have coherent political and societal debates on this subject. I've kind of already touched on this, but when we think about predictions, I think climate predictions, we usually think about predicting changing temperatures, changing rainfall, maybe changing heat wave frequency, maybe changing crop yields or health impacts, something like that. I would say that climate predictions need to go much further than that. We ought to be painting a picture of what our societies will look like as a consequence of climate change. So what I mean by that is certainly some of the work that I've been doing recently is focused more on saying, well, okay, you get these warmings, you're going to get increased floods, you're going to get increased heat waves, but in a sense you can look at that and say, yeah, you know, we can probably have engineering solutions to lots of these things. You can build flood defences on rivers, we can put in air conditioning, we can do lots of things. I think my point would be, if you're continually being hit by floods, by heat waves, by whatever it is, by changes in crop yields, there will be a continuing demand on our governments, because we look to them to support us, to help us recover from those. So you're going to be continually spending to recover from this flood or that heat wave. And that is going to be an increasing drain on our economies. So if you're spending on that, essentially you can't spend on social care, you can't spend on education, you can't spend on the health service. It's going to be a continuing degradation of the facilities that our society provides for us. And for most people, it's not that you're going to be hit by a flood, it's that you're going to feel that continuing degradation of the society that we're living. And that's what I see as the prediction. That's the sort of thing that we need to be talking about. Okay, so it's all about prediction, but it's not about prediction as well. It's about a particular sort of prediction. It's not about predicting something like the roll of dice or tomorrow's weather. This is a crucial thing because there's a lot of work on relationship between weather forecasting and climate forecasting. But these two things are fundamentally different. And in particular, they're different because predicting climate change is about predicting a system whose state is fundamentally changing. Predictions of climate change in the 21st century are a matter of predicting behaviour under conditions that we have never seen before. Now, you're all, in a room like this, you're all going to be familiar with a plot like this, but just put this in your mind. This is the last, I'm sure you've all seen this plot. This is carbon dioxide concentrations in the atmosphere over the last 650,000 years. It's pretty much the same for the last million. You get in and out of ice ages. But the point here is, for the last 650,000 years, we've not been below about 180 parts per million. We've not been above about 280 parts per million. And anatomically modern humans have only been around since about this point in time. Human civilization since about this point in time. So we've lived in an incredibly stable period But since the Industrial Revolution, we've now gone up to 420 parts per million, and if you include other greenhouse gases, up to about 454 parts per million. We are way outside anything that the planet has seen in the last 2 million years. Now, that can be said to sound scary, I mean, it is, because this controls the amount of energy that's being trapped in the system. But what I'm just wanting to point out is that it means our observations that we have of the past, even if they're in this period here, the last sort of century or something, are of observations of the system in a different state to what it will be in the future. That means we shouldn't expect that we can just take our observations of the past and use that to say this is how it's going to behave in the future. So think of this as if you've got a kettle and you're observing a kettle and it's warming up, you observe that it warms from 60 to 90 degrees in a minute. If all your knowledge comes from those observations, then you would say, well, in another minute it's going to reach 120 degrees. But of course you know it's not going to reach 120 degrees because we know about the physics of water, and we know it's going to boil. This is actually pretty crucial to how we do climate change science. It's important in the physics because when we looked at our climate models don't compare well with observations of the past. But even if they did, that wouldn't necessarily give us confidence that they were reliable sources of predictions in the future. And similar arguments in economics. There's lots of work in economics that says, well, how damaging is climate change going to be to our societies? The people in the econometrics community will go away and they look at the behaviour of different societies around the world, where there are different average temperatures, and perhaps even say, well, how are these temperatures changing in different parts of the world? And we'll say, okay, so we can see how climate change impacts GDP. Well, okay, but you can't use that to predict. That's not. We take going into a different state. You can't just use that and say this is the sort of damages that we should be expecting. We need instead to consider, like water in a boiling kettle, we need to consider processes. We need to consider the actions, the interactions. And we need to think about how the physics and in economics interact. And we need the imagination to just think about how the different processes of societies and of physical systems work. There's an awful lot about imagination here, and that doesn't sit well in the scientific research community, but there's a lot about imagination here, to being able to draw ideas together, and I'm going to say a little bit more about that at the end. So my third characteristic is that climate change is a one-shot bet. We can't predict the future precisely, of course, for many reasons, some of which I'll come to in a moment. So when we talk about climate predictions, we have to consider uncertainties. So that means at best, a climate prediction, at best, is a probability distribution. So that might be saying, well, if there's a 90% probability that the change in temperature at some place might be between 3 and 6 degrees, or maybe there's a 70% probability that the fall in GDP will be between 1 and 2%, maybe 10 and 20%. These are certainties here, very big. And so we have to think of it as a probability prediction. But of course, probability predictions are not unusual. I keep being told that the public don't understand probabilities. I just don't think this is true. All my experience is the public do understand probabilities. They've got a really good familiarity with them. And probability predictions are used all over the place. They're used in the insurance industry, they're used in betting, they're used in everyday life. But usually when we use them repeatedly. So in the insurance industry, for instance, they have predictions of the hurricane activity in the next season, but they'll get multiple predictions through the season, and then they'll have similar predictions the next season, and the next season, the next, and they will use them at different stages. So they're repeatedly using these probability predictions. And similarly, on a sort of small scale, I talk about in my book, sort of the time it takes me to cycle to the station. You'll know this. You have an idea in your head. You might not have drawn it on paper or worked it out exactly, but you know roughly not only how long it takes, but also what the margin of error is. And that helps you make a decision of when to set up. You make a judgment of kind of push it here. Sometimes you get lucky, sometimes you get unlucky. But on average, if you've got a good probability prediction, on average, then you're going to make your choices well. The problem with climate and climate change is that's not what we have. You might make a probability distribution, and that does tend to be what we do. We have some probability distributions for how climate is going to change through the 21st century, but there will only ever be one 21st century. You do not get to play it out again. So there's kind of a big question there. How should you be using these sorts of predictions? It raises questions. Doing well on average is not what we're looking for. It raises questions of how we respond to risk, and particularly how we respond to existential risk in terms of our societies. Which brings me to the fourth characteristic, which is nonlinearity. So a lot of my book is about nonlinearity, it's the connections with the maths of nonlinearity, and many of you, I imagine, will be familiar with mathematical chaos, the idea of the butterfly effect. So this is the idea that as Ed Lorenz said, if a butterfly flaps its wings in Amazonia, does that affect whether you're going to have a tornado in Texas? And the point there is not that a butterfly's wings flapping creates a tornado, it's that it leads to a chain of connections and interactions that influence whether there is a tornado or not at some point in the future in time. Now, this sensitivity to those, this is saying the future is sensitive to your starting conditions. And this sensitivity is incredibly important for weather forecasting, but it's often assumed not to be a crucial source of uncertainty in climate forecasting, because it's this sensitivity that actually gives you the probability distribution in the first place. So you might take a model and you'll run it many times with slightly different starting conditions, and they produce different futures, and those different futures produce the probabilities of what could happen. So this is kind of all well known. It all sits within a sort of standard framing of mathematical chaos. We know about nonlinearity, basically nothing to see here. But the problem is threefold. First is that the probability distributions, the predictions, the probability distributions that we have for the future, they themselves are sensitive to how you set your model going. So it's not just where you are within the prediction, it's the probability predictions themselves. And this has been very little studied. There are only 2 or 3 papers that have begun to look at this. And yet it can have a big effect on the predictions you make. Second is a more philosophical aspect. If we had really good observations of everything we wanted throughout the climate system, throughout the oceans, throughout the land surface, and as well as the atmosphere and the upper atmosphere, if we had really good observations of the state of the climate today, we still wouldn't know what was the best way to start our models off, because our models are different to reality. They have different things in them. In mathematical terms, their tractor is different to that of reality. So there will probably be more informative starting conditions to set your model going from, more informative than others. But they won't be the same as the observations. So we have a big challenge there. How do you take observations and our knowledge of the climate system and say, this is how we should be starting our model simulations? And then the third point is that the nonlinearity aspect here doesn't just affect the consequences of the different starting conditions, it also affects changes in the model structure, how you build your model. It might be that even the smallest of changes, the smallest of errors in the formulation of your model could lead to different probability distributions, different predictions of the future. That's something that Erica Thompson has called the hawk-moth effect. And he kind of says, it might be that even if you have a really, really good model, but it's not perfect, you still might have really flawed predictions. Now, we don't know if that's the case. That might or might not be the case. At the moment, our models are so far away from reality that it's not something we necessarily need to worry about too much. But it raises the question of just how good a model do we need? How good does a model have to be? And there are parallels of these issues in the economic systems and the economic models that we use as well. Okay, so characteristic 5 is the lure of powerful computers. So we live in an age, the last 20, 30 years, we've seen this rapidly, massively expanding availability of computer power. And this has dangers as well as opportunities. It clearly gives us many opportunities. We can run more powerful models, more detailed models. We can include much more in them. But it also leads to an awful lot of the research funding, an awful lot of the research effort going into simply getting these models to run, of basically filling up the latest computer. Buy a bigger computer and now put a bigger model on it. And it distracts from thinking carefully about what we need, what models we need, what we want the computers to do, what is the best use of this computing resource. I was going to talk a little bit later, but I think I'm going to have to cut it out, so I'll put in a few comments here. I wrote a piece in The Guardian a few weeks ago, which argued that this push towards really big computers, there's a big push towards spending billions on very large computers to give very high resolution climate models, when the argument here is that these will provide the sort of detailed information that we need for climate adaptation. My argument is that they won't, because there'll be high resolution in the atmosphere. They look really good. The pictures you'll get out of them will be very, very pretty. But we haven't really worked out what we need from any of these models. So, and I would argue aspects of the ocean biogeochemistry, ocean circulation patterns, ecological systems, there's no answer to quite what we need there. We haven't really addressed the question of what we need in a climate model to be able to give reliable information. And indeed, many of my arguments in the book is that we just shouldn't be going down that path. We should be looking for diversity. We should be getting, we've already got pretty good models. I don't think improving them is going to take us very far, but we can explore what different models can do, and that can help us understand what plausible futures there are. The sixth one, the penultimate one, is multidisciplinarity. I've sort of touched on this quite a lot. I would argue that few aspects of climate change can be studied robustly without being guided by a wide range of disciplines. We need, this is very obvious to me in working in the London School of Economics. In the researchers in climate economics don't tend to understand the foundations of the physical aspects of climate change, and therefore don't understand the uncertainties in the physical aspects of climate change, and therefore produce assessments of the economics that don't reflect those uncertainties. That's a real problem. But the physicists in the audience, if there aren't any, shouldn't feel smug about this, because I would argue that in order to get good information, the physical sciences ought to be directing their work towards what is relevant to society. And they might think they know that, but just like the economists don't really know what's going on in the physics, the physicists don't tend to really know what's going on in the economics or in the social systems or how they interact, and they need to be more directed by that. But there are more practical aspects as well here. There's There's aspects of the nonlinearity, the maths of nonlinearity. There is expertise there where people have some understanding, and yet they're studying slightly the wrong problem because it's mathematically soluble. But they have expertise that would be valuable in the economics and in the physics and in the modelling if only they talk to each other. But they talk different languages. They don't come together. So there's expertise, there is understanding out there, but it's not being brought together. And then finally, this kind of the obvious one, for you guys, I guess, particularly, is just the urgency. Climate change research is not just an academic problem. It matters for society, and it's a matter of urgency to be clear about what we know, what we don't know, and how we expand on that knowledge, what we can potentially know to give us better answers. So I see this as a sort of context of the history of science. Science doesn't just go towards an answer, get an answer, and then you sort it. It goes down all sorts of blind alleys and does things incorrectly for many years. The example I've got here is just a picture of the solar system, including the planet Vulcan. The planet Vulcan was proposed to explain the oddities in the orbit of Mercury. Same thing had been done and led to the discovery of Neptune. And so very successfully, and then Neptune was found. Oddities in the orbit of Mercury was used to deduce that there was another planet, Vulcan, and so people went out to look for it, and they found it. There were observations of it. Those were quietly swept away when it became clear that it actually didn't exist, and that relativity just explained the oddities of the orbit of Mercury, and you didn't need another planet there. But this is just one of many examples of how science takes the wrong trajectory at times. This isn't a criticism of science. This is a power of science. We do this, we find things out, then you move forward. But climate change is a problem here because I can't dismiss it in that sort of, we might get it wrong for 60 years, but nevertheless we'll work it all out in the end. If we do that, then it's just too late. The science is irrelevant. So this use of models becomes really important. How we use it, if it weren't for the urgency, I would say, well, it doesn't really matter. We can get it wrong. We'll do our best. We'll write a paper or two. Maybe we've got it right and somebody else has got it wrong. Maybe they've got it right, and people will look back and say, weren't they clever? But it doesn't really matter. But this matters. So reflection on quite what we know and what we don't know seems to me tremendously important. So those are my 7 characteristics. Out of these, they lead to a set of challenges. Not surprisingly, I'm running a little bit over. I did start a little bit late, so but I don't really have time to talk about them, so I've mostly included them because I'm always a little bit paranoid that it seems horrific to me if I just don't have enough to talk about to get to the end and sort of say, oh well, I've got another 20 minutes. So I put in some slides on this, but I don't really have time to talk about it. But I've got some of these here. I was going to highlight 3 of them, which were how to balance justified arrogance with essential humility. There are a lot of aspects to all of these questions. One of the aspects to that is simply how we communicate climate change, sort of being clear of what we know, what we don't know. But even when we're within the scientific community, within the research community, there are aspects here. So you could talk, for instance, about how we go about understanding climate sensitivity. That's the response of climate to doubling CO2, sort of measures how sensitive climate is. There's a lot of work there that uses observations of the past or that uses models in a way that I think misleads us into thinking that the sensitivity is more constrained than it actually is. There are huge issues about how we relate models to what will happen, and issues about how we relate information, how we use the information we have, or what we could have, to build a better future. Okay. So I want to finish with three thoughts, or 3 concluding remarks. One is just about this aspect of uncertainty. I would argue that uncertainty is at the core of climate change and is at the core of climate predictions. But we need to approach uncertainty differently. We tend to talk about uncertainty as if we have some prediction and then there's some uncertainty about it. It's sort of, it's got this great prediction, but it's not quite so good. The uncertainty measures how not good it is. And I think that miscommunicates the character of what we're trying to do here. The uncertainty is the information. The uncertainty is at least part of the information, but I would say it is the information. And our knowledge of the uncertainty is crucial for responding well to climate change. And I feel I've been led over the last 20 years, particularly in the early stages, down the wrong path of being told, don't talk about the uncertainty. The uncertainty is the information. And a policymaker or somebody in industry can't make good decisions unless they have the uncertainty information, because that is the information we have. So don't hide it. It's not a tweak on the best estimate, it is the information. The second point I was again made was just to come back to this point about imagination. So back in 2008, the Queen, so you remember in 2008 there was a large financial crisis at the time. The Queen went to LSE and she asked them why it wasn't predicted. She said, if these things were so large, how come everyone missed them? And so the professors at LSE went away and gathered a group of people from around the world that they called the Global Financial Crisis Forum, and they got together under the auspices of the British Academy, and they debated for some time, and then they came back the next year and they wrote to the Queen and they said, it was principally a failure of the collective imagination of many bright people to understand the risks to the system as a whole. And I think I see this throughout academia, really, and certainly in climate change. There are many, many bright people who understand parts of the system very well, but we are not good at drawing that information together and understanding the system as a whole. You can't just bolt them together. You actually have to talk to each other and understand what are the foundations of the different sources of knowledge. I'm not sure we have sufficient imagination at the moment, and we need that imagination. We need to be drawing it together. And then finally, a word on values, unless you want me to stop now. Okay. So this comes back to electorates. It comes back to sort of people. I think we need to work out our own opinions on climate change based on personal values, but also based on what is known. So we need to be able to separate these things are known, these things are open to debate, but also give people the opportunity to see that information through their own values. We need them to be able to bring their perspectives to the table so that populations, electorates, individuals have ownership of the problem. I do worry that climate change is almost has been seen as something academic. The academics understand it and they tell us what to do. It's kind of too big for that. We can't have this sort of, now you need to do it. And a lot of academics that I talk with are very, very frustrated about the lack of response in society, and yet they're not really interested in how society works. And unless you engage with that societal side, unless you give people some sort of element of power, then it's difficult for me to see how there will be big changes. So that means being clear. Some things are about values. People will have different values, they will value the future differently, they will have their own stresses in their own lives, there will be all sorts of other things that they care about. It's about portraying climate change through these different lenses and allowing them to bring their values to the table, while also not allowing what we've also seen in the past, the skeptic kind of view of denying aspects of the science that really just shouldn't be denied. We need to be clear that some things are just known, and there's some things there in the social sciences as well as the physical sciences. So to do that, I think getting the best possible information really matters. So all these things I talk about in my book and talk about today, I think really matter. if there's stuff that we don't understand today, that's just not in the realm of human understanding, c'est la vie. I'm not going to worry about that. That's a kind of asteroid thing. I'm not arguing that we should resolve issues so that we have understood everything. There will be things we don't understand. That doesn't worry me. But if the information that we have today is limited because we aren't combining the information that we already have in different disciplines, in different places, but we're just not bringing it together very well, then I think that's bad. I think then the message is we should be doing better. And there are lots of those foundational questions. They're kind of in the book. They're kind of, this is exciting, who knows where that's going to go. But there are also lots of opportunities to improve information shorter. So it's kind of, the apples are on the trees at this time of year. Some of them are way out of reach up at the top, but some of them are down low. There's a lot of low-hanging fruit. We could be doing things a lot better. And I'd like to think that my book describes something better. Thank you very much.
Thank you so much for that talk. It was so fascinating, especially the bit about uncertainty being the information that we've all been waiting for. I think now we'll have a panelist come up and we'll start the panel discussion. If you have any more sliding questions as well. So let me introduce the panelists we have for David. But so we also have Stuart Jenkins, who is a research fellow in the School of Geography. Stuart's expertise lies in achieving net zero emissions in the fossil fuel sector. His recent DPhil delves into often overlooked non-CO2 contributors to contemporary warming, an essential aspect of climate challenges. And Sharon Ermis is a DPhil student in atmospheric physics. Her research focuses on extreme weather events, such as windstorms, and determines the impact of climate change. She is also co-president of Oxford Climate Society and is passionate about communicating climate science more effectively. So we have a couple of questions, pre-prepared questions that are open for the whole panel, but then we'll move on to the Slido one, so make sure you've sent them in. Do you want to switch that? Oh, show that.
Can someone maybe put in a test question and then we can see if the question comes up?
Yeah.
I think you need to put it into the question and answer bit and not into the question about what you associate with recommendation. Thank you. You can also vote on the different questions. If you want a particular question that's already been asked particularly much, then you can vote on it.
Awesome. So, David, in your book, you highlight how important it is for climate science to be multidisciplinary in order to ask societally meaningful questions. So my question to you guys on the panel is, how can climate scientists ensure that the research that they're doing is useful for adaptation or mitigation efforts?
Do you want me to start?
Yeah, sure.
How do climate scientists?
Mm-hmm.
I think there's twofold. It's kind of what I was saying earlier. I think one is to question your assumptions. really track the assumptions in any conclusions you're drawing as far back as you can go. So, so if you're using models, if you're using multi-models, raise the assumptions of quite what are the limits of what you're providing, so that you can be clear on these limits. I think that is crucial. And the other is putting the time to talk to people who actually are involved in adaptation. That's far easier said than done. It's a bit of a trite answer, to be honest. It's almost impossible to, but that's, in principle, that's what one should be doing. I think historically, what we've tended to do is produce information from climate science and hand it over. Like, there you are, work out how to use that. And to be really useful, track the assumption, then go and say, okay, is this useful? What aspects can I present differently to make it useful?
Yeah, 100%. I think we've seen kind of like the fragmentation of different disciplines, like even within geography, physical geographers and human geographers being in separate buildings sometimes, like overcoming that.
It's usually the way, isn't it?
Yeah.
Which is understandable, but it's problematic.
Yeah, I completely agree. I think that you can see it even within, when you can see the fragmentation within an institution, it does kind of display how difficult it is at a societal level to make all those connections and have all the people in the room that you need. And I think, when you see it even within Oxford, even within physics in Oxford, there's 6 sub-departments and they often don't sit in the same building. Having that wider collaboration and the appreciation of what knowledge you need to answer the right question, as opposed to just answer the question that you perceive, is a challenge. I think it's maybe about reversing. Climate change is such a societal issue. You really need to reverse the question asking process as an academic. I think it's not good enough to create the question from academia, resolve as best you can that answer, and then send it out. You need to reverse it and go to the stakeholders and ask them what information they're missing, because that should be, I think, what we're trying to provide.
Yeah, I completely agree with that. That's actually some of the things that I've written down for that question as well, because it is a constant struggle in when you have your own research project to reevaluate whether you're still asking the right questions. With the research that I'm doing, we have like an initial starting point of what we want to do, but then each step kind of requires us to think again, like, are we still focusing on the right variables in the climate model? Like, do we want to look at wind gusts or wind speeds, or like, it sounds very minor, but it can make a big difference for people that are actually using that information. And then, yeah, it's a bit disappointing almost that it's not more supported. I think maybe you discussed this in the book as well. It's like, it's almost like an extra job that you have to do on top of the actual research that you're doing, because it's usually not supported to go out to stakeholders and actually talk to them. So yeah, it's a constant struggle to actually make sure that you're asking the right questions.
Thanks for getting that. I was just sort of thinking I hadn't said that. And that's absolutely right. It really is. It's bizarrely annoying. I don't know whether you see this sort of, because it is encouraged. People think it's great, go out and do this, but it's always an extra. It's not supported. It's not at the core of, it should be at the core. I would perhaps also, this point about talking to stakeholders I think is really important, but I also think often they don't know what they need, or in particular they don't know what can be provided. So this very much goes to my uncertainty and confidence sort of line, so they will not know about that. So it's a matter of having the conversation, because if you just go and say, tell me what you need, they don't really know. So they'll come back and say, well, tell me everything. Hence, that leads us back to the big models of will tell you everything. But actually, if you sort of say, well, okay, we can provide this is something we can be confident about, then I think often you'll find they'll come back and say, well, that's interesting. Well, it's not quite what we need. Can you provide that? And is that negotiation?
You don't even want to get to that point, right? You want to already, when you're doing the research, ask the right questions. So it should probably be a continuing conversation.
Yes. Absolutely.
So So a large part of the uncertainties when it comes to predictions is that we don't know what future emissions are going to be. Where exactly or within which industries do you believe the biggest uncertainties are when it comes to climate change mitigation, and how can we begin to tackle these?
Do you want to take that first?
Yeah, I'll have a go. So it's a challenge in a way to pull the problem apart to a particular subset of society. I mean, well, I can give it a go, but I'm sure we'll disagree. I think one question that I'm really racking my head over at the moment, how a fossil fuel producer responds in a transition. So in a world in which the fossil fuel production, the fossil fuel demand has gone down and the price of the fuel has changed, what does the producer do? How is it reacting? And that is a real uncertainty in our modelling of the future, I think. And there's a lot of models are based on a welfare optimization, which essentially comes down to a cost optimization problem for developing a trajectory for society. But it devalues those aspects of how society chooses to react in that situation. So, for example, Saudi Aramco, the national oil company of Saudi Arabia, have more additional capacity, so they can turn the taps more on by more than the total production capacity of Shell as an oil company. That's the scale of that as an organisation. So in 15 years' time, when we're in the middle of a transition, the oil price has changed dramatically, the demand for oil and gas has changed dramatically. How that organisation chooses to respond is absolutely vital to our prediction of the future, and I don't know how you constrain that uncertainty.
Anybody have anything to say? Do you want to ask that question?
No, I think it's a really difficult question. I think it goes to how we manage our societies as a whole, and the relationship between governments and industry, which feels like a tricky place to go, particularly since I've not thought about it particularly carefully. But it's exactly these problems that arise because you're looking at something in the market forces way. It's saying, if you have an industry that says, this is what I'm trying to do, I'm trying to perpetuate my industry, I'm trying to make profits for my industry, then you know something about how they will behave. How we regulate ourselves to manage that.
I do think that the solution is it is moving beyond the market-based framework. So if you look at a lot of climate policy today, it's based around providing some sort of compliance framework and penalising failure to comply. So things like the European emission trading scheme, it's exactly that structure. It provides a price for CO2 and a non-compliance penalty, essentially. But it's not a regulation. It provides no means to actually regulate additional CO2 production. It just makes you pay an additional fee if you produce more CO2. And I think we need to talk about additional policy mechanisms that actually regulate producers and suppliers of fossil fuels as well.
But I would reiterate, you've got to have electric buying, because what that's doing is, I mean, essentially what that's doing is putting up the price of energy from fossil fuels. If that puts up the price of fuels that we use to live, then we don't like that. We don't like the cost of living going up. So there's a whole mixture there of the investments in the alternatives, which of course we're doing quite a lot, but there's also an acceptance of that. I think maybe I think I'll be interested in your views here. So I don't quite know what I'm talking about here, but I think there's a sense in which we talk about win-wins. There's all sorts of things we can do. It's not going to be a detriment to society at all. It's not going to cost us at all. It's the green premium. It's going to be lovely. We can have things that are lovely, and it's not going to cost us a lot. It's just a matter of deciding to do it. And I don't think things are that way. I think there are elements that are. There's a huge amount that we can just do that are worthwhile, and absolutely. So yeah, we absolutely should do that. And I'm not denying that. I don't think that takes us anywhere near the whole way. And so that means we need buy-in for fairly significant structural changes to our societies.
Again, maybe I'm also not the expert on this, definitely not. But I feel like that might be true in the long term. In the transition, yes, we do need to pay for that transition, but long term, there are probably going to be benefits for most people from having renewable energies and then hopefully cheaper electricity. And there's all sorts of intersections with climate change and poverty, for example. So I feel like we need to make clear to people that ultimately this will probably have loads of benefits and more benefits than costs. We just need to make sure that that transition is fair and that we, I guess, make the right people pay for it, hopefully. That's my sense on that. That's the personal opinion.
I think that's probably right. I think it's, I agree with that. I think it's just important to be clear what people are buying. So it's sort of, if you're asking people to pay, then yes, there are benefits that they get from that. We should be clear about that. This is it's kind of, you should be willing to pay because this is what you're getting. It's a good thing. It's a good thing to do that. I was speaking to a colleague recently, so I think it really worries me that it's being recorded. But I think there was one of the government ministers talked about how the British public shouldn't have to pay for I can't remember, the green transition or something like this. And I think my thought there was that no, they should, but they should be willing to. It should be a matter of, you should see why. If you're just saying pay because we're telling you, they're not going to be very happy. But actually, they're buying something for that. They're buying a better future. There are these benefits. There are lots of benefits that you get from this. It's not just a matter of paying, but it's not portrayed that way. And I think that's problematic.
Super interesting discussion. So I think maybe we'll move on to some of the Q&A questions because we've only got about 20 minutes left. So the top question is, by embracing uncertainty in climate prediction, how do you think this can be framed to minimise potentially negative reactions from the public?
I guess that's one for me to start with.
Yeah.
I think two things about that. One is, I think there's an awful lot of the public that are uncomfortable with what they hear about climate change and climate change science because it doesn't feel reliable. And that's because of this absence of government uncertainty. And there's a kind of silent, large group there. They're not climate skeptics. They're not that they doubt there's warming. They're not that doubt's going to be disruption. But they do question whether the scientists are being honest here, because it doesn't feel right. So I think there's a huge benefit in dealing with uncertainty, because I think you will get on board a lot more of the public. So that's one aspect. Nevertheless, there will be inevitably something of a backlash if you deal with uncertainty. In this country, my sense is there's far fewer skeptics than there were 20 years ago, but I always worry about that each time I think that 3 weeks later I hear somebody saying something loony. They will use it if you have bad actors that just want to manipulate the information. They will use it as a portrayal of that scientists don't know anything because of this uncertainty, and that will be challenging. I think we do need to just face it head on. I think it would be better if we'd faced it head on 20 years ago. I think there's been from 2000 to 2010 or so, I think there was a lot of basically running away from the skeptics, and beyond that actually. The skeptics worked, they were successful because they stopped scientists talking about the uncertainties. And that was disastrous. It was disastrous. It's really undermined the debate over the last 20 years. My feeling is still, though, that unless we start, we won't get out of that barrier and get the bulk of society on board. And we need the bulk of society on board. This should not be a partisan issue. It needs to not be a partisan issue.
I sometimes worry that the problem isn't actually that we're not communicating things right as scientists, but that there's a lack of statistics knowledge in the general population, that people haven't really learned how to deal with uncertainties, and that maybe it would help if, for example, the media wouldn't pick up so negatively sometimes on us trying to roll back and not be super certain, but actually say, well, there is a certain span of uncertainty here, and that's just what it is, instead of focusing on the mean and the one result and the one number that comes out of the study. So yeah, I feel like it's about the communication, but I feel like we need to embrace statistics a lot more and actually be willing, or like also understand that the general population might not know about this for very good reasons. They haven't been taught statistics very much, and so getting them on board and making them understand that they can understand is actually understandable. Important.
And I think just touching on that, perhaps worse is when you see a headline that has taken the 5th percentile of a distribution or the 95th percentile of a distribution and used that to communicate a risk that is substantially more nuanced, perhaps, than the media are given credit for. And it's a twofold thing, because greater interaction between science media and scientists would go a long way to improving the discourse that the public actually consume, I think. But it is frustrating that when that happens, and then to the best of a colleague a few years ago published a distribution of time remaining to 1.5 degrees, and then the number that's jumped on is the 90th percentile, and that's not a useful discourse. That's one point, I guess. The second point was I really liked the discussion of to what extent is the uncertainty information in itself, and to what extent for the climate issue is the uncertainty particularly informative because of the existential threat. So the 50th percentile isn't necessarily the value that you should be thinking about if you happen to wander into a world which is at the 75th percentile, and that's catastrophic. And I don't know if you've got some thoughts on how do you think we should treat predictions and projections, perhaps, of the future, distributions of future temperature rise in a scenario in which there is that unknown tipping point, threshold behaviour?
Um, well, I think it's kind of even worse than you did. So if I go back to what you were saying about picking out the 95th percentile is problematic, and you're right. However, I do talk about something in my book. In climate-prediction.net, we had so climate-prediction.net had multiple different versions of a model, and we ended up with a whole collection of models. But we thought long and hard about what that meant. So that gave us a distribution, but we thought long and hard about what that distribution meant and came to the conclusion that that distribution meant virtually nothing. That where most of the models were in the results was simply because they were closest to the original model. So when you start a model and you start changing it, most of the changes don't make any difference. So you've got lots of models that are like this first one, but then that's not an indication about reality at all. So we felt that actually the only thing that had any meaning was the range of behaviour. So if you've got a probability distribution, you can have the 95th percentile, but if you don't, if you just have lots of odd samples without probabilities, then you only have a range. And we highlighted the range. And some people didn't like the fact because they assumed it was a probability distribution. So this is actually a conceptual thing of the kind of philosophy of models. It's sort of how does a computer model tell us about reality? So we've come quite a long way from your starting question. So I would argue what we know is that sort of range. In my sort of ideal world, I would present people with that range, particularly decision makers, people who are building things, whatever, and they then have to make a judgment. So if the increase in height of river flows is going to be between 40 centimetres and 3 metres, then that just is what it is. In my ideal world, they could take that information because they would then look at, quite literally, the lay of the land and work out what options they have, where they can put their barriers, and say, well, actually, we can do something for a metre quite cheaply, but if we spend a bit more, we can do for 1.5 metres and have flexibility to go way beyond that. And the fact that you're telling us 40 centimetres, 3 metres sort of says, actually, we should take that second option. We're not going to invest in a whole 3 metre barrier, but we are going to invest in something that has that flexibility to be upgraded if that's what we need. Now, that assumes a smart decision maker. I've met quite a lot of smart decision makers. I'm not quite sure whether that works for the tabloid press.
So the next question is, how do you think academia can change to be more imaginative? And who's best positioned to lead this challenge?
How can it change to be more imaginative? So this changing to be more imaginative is very closely linked to being more multidisciplinary. It's bringing the disciplines together. And that's a very fair question. It's a bit sad that I don't really have a strong answer, but I think it's about recognising it. It's about the research funders recognising multidisciplinarity as a core area of research, and that it is blue skies multidisciplinarity. So much multidisciplinarity is kind of, well, you do a bit of physics, can you talk to this industry? That's not what it's about. It's about exploring our understanding. So the research funders have a lot to do there. But more than that is universities. It's universities recognising and giving credit for doing multidisciplinary work, and it's not what I see when I'm in meetings about how career progressions and things. They're sort of, you just see this department saying, well, yes, we love multidisciplinarity, but you've got to have your 4 core papers in these journals in economics because you're in an economics department. If you haven't got them, then we're not going to consider you. And in practice, the only way you're going to get those is if you don't pursue multidisciplinary approach. It's set up for that to fail. And unless it's kind of how to do this, I think you need the vice chancellors in this country. You need the vice chancellors to come together and pretty much have a pact and say we're going to change that. Alternatively, you could perhaps have a large centre that you could get together. I mean, you have a large centre that says actually we're going to do this. We're going to provide jobs for 10 years for groups from very different disciplines, and we're going to put them together. We're going to see what we can do. It's kind of like I mean, people talk about a CERN for climate, by which they mean large models, largely. But I would say this is more like a Manhattan Project for climate, saying you're just going to put a load of people together and say, do your best to come up with something really good. So you kind of need a big philanthropic fund there to do that. It's a huge challenge, but it's recognising that it's a challenge is the starting point.
I mean, I don't know much about that very high level, but on the smaller scale level, I really found it quite helpful to have supervisors that have studied different things, and that's actually quite nice. So that's probably something that probably almost everyone can do as a PhD student. It's quite a nice opportunity. I would also say that because climate change is so asked for, or knowledge on climate change is so asked for by government, it's quite a unique field for multidisciplinarity. My PhD project, for example, was for the Met Office, and that's a really nice example of, it is part of the government technically, but they are asked questions, and then there's scientists there as well, and they are kind of in communication and they're in the same building, which is quite nice and creates really good dialogue sometimes. So it is kind of good for that sometimes, not in every sense.
Yeah, I mean, I agree with all that's been said. I don't know if I've got anything particularly useful to add. I think that you can see the frustration within an institution in the requirement of a department like biochemistry to do work that's between biology and chemistry is a sign of the frustration of the institution and not being able to collaborate, I think. And you can see it time and again in discipline after discipline when a research question arises which falls between the cracks instead of there being a collaboration in academia. There is so often a new institute that's required to make that work happen, and that's really frustrating. And climate change is really at the fore of it, because as you say, it's so important to take that breadth of understanding. It's not good enough to just have the physicists sitting in their room and thinking about the solution. In terms of how we resolve it, I think a Vice-Chancellor's statement would go a long way. I think that funding decision makers could perhaps be more imaginative in what they deem to be a funding partner, and when external partners outside of traditional academia are brought into the process and allowed to actively collaborate on a research question, would help perhaps bring multidisciplinary thinking more to the fore. But it's a difficult problem to solve, for sure.
Can I throw in one more barrier? So I think researchers, academics are barriers to this. When I see reviews of funding proposals, of papers, academics are awful at thinking across disciplines. And so if you have some sort of multidisciplinary paper, multidisciplinary proposal, you will tend to get reviews that come back and sort of say, yeah, this is kind of great, but it doesn't do as much of my stuff. It would be better if it did more of my stuff. And you can have 3 different reviews from different people, all of them saying that. And into different areas. And the problem is that when that's assessed by the funders, what you have is it's kind of okay from 3 people, and you're not going to be funded with kind of okay. You're going to be funded if this is brilliant and groundbreaking. But they don't, yeah, we shoot ourselves in the foot. I try not to.
So I think that kind of brings us to the end of our time. We've got about 3 minutes left, unless you think we quickly discuss.
No, I think I don't want to not on camera.
So thank you so much to our panelists for joining us. And yeah, just a reminder that the books are on sale. So
Thank you so much.